Consider a simple graph of equation y equals x squared. This graph can be represented by this simple mean squared error loss equation. But remember, this is not just simple y equals x squared graph, but loss from predictions with respect to actual outputs. It consists of two values. Here y hat is prediction from the neural network, and y is label from the dataset. This is simple equation represents the loss calculated using both label and prediction. Here on x-axis we added prediction, and on y-axis we added loss with respect to prediction. For initial value of prediction y hat at 1.5. Now if prediction at current point is 1.5 and loss is 0.25. If we change the value of prediction, you can see that loss also changes. The question is, at a given point, should we increase the value of prediction to reduce the loss at given point? Or should we decrease the value of prediction to reduce the loss? Also, how much should we increase or decrease? For that purpose, we calculate the derivative. This value simply represents the derivative of loss with respect to prediction. Remember, loss depends on only two values here. Label here is static value from dataset, so it cannot be changed. But prediction can be changed to reduce the loss, right? This is the reason why we calculate the derivative of loss with respect to prediction only. You can see derivative of loss with respect to prediction is positive. Its positive sign tells us to decrease the prediction to decrease the loss. You can see that by decreasing the prediction, loss decreases. Now you can see derivative of loss with respect to prediction is negative. Its negative sign tells us to increase the prediction to decrease the loss. So by increasing the value of prediction decreases the total loss. But there is just one point where the loss is minimum and gradient is 0. But we are here to discuss local minima in mean squared error loss, right? Let's add another graph. Now this is where the situation gets interesting. We have first input of 2.0 and second input of 3.0. We also have weight W1, and now this is parameter in equation that can be changed. This equation gets inputs and weight to give us y hat. This y hat will be used to calculate the loss mentioned above. Remember, this equation is not a neural network. I just used it with one weight because it's easy to visualize. You can imagine a neural network instead of this equation. Here x-axis represents value of weight, and y-axis represents value of y hat. This is same y hat which we are using in above loss function. You can see how just by changing the value of weight we can increase and decrease the loss in first graph. This is because y hat used in above equation is same as y hat we get from inputs using this equation below. Now fact is that this is just one function. To understand this, let's just combine these two functions. This equation, which is combination of previous two equations. You can call this equation as mean squared error loss equation. Here you have first input I1, second input I2, and one weight just like previous equation, and label for calculating loss. As you can see, this is same mean squared error loss, except that this now have actual prediction equation replaced with prediction value. Also for labels we now have W1 on x-axis and loss on y-axis. Now derivative of loss is calculated directly with respect to weight W1. You can see we have a local minimum value where our model can get stuck. We use optimizers to solve such issues. But now here is the twist. We can have different inputs of dataset to minimize loss for each one of them. And we can also have different labels for different inputs also. And also, what about multiple labels? These changes can change the function we want to minimize. We will further discuss about the topic in next video.